Today we're going to be discussing a concept called rate of change. And rate of change can be discussed in the context of other kinds of functions, but today we're going to be particularly interested in looking at the rate of change as it relates to a line. And so this can also be called the slope of a line. So when you see the words rate of change or the word slope, you know that they can be used interchangeably in terms of lines. We have a graph here on the right hand side which gives us the population of the United States from years from 1981 to 2011. And we see that the population here is given in millions as indicated by this graph, and that it is indicated to be 230 million and 313 million at these two different points in time. So what we're interested in is how did the population of the United States change over the period from 1981 to 2011. So we're going to use our information and we're going to find the rate of change in this population of the U.S. from the given time period 1981 to 2011 or 2011. So how has the population changed from 1981 to 2011? Well, one thing that we can observe from the graph is that this population has been increasing. So we've got a situation where we're seeing over time, as time goes by or gets larger, if you will, so does the population. This is actually called a positive slope, and we'll take a look at that in just a couple of minutes. But in order to do this mathematically, what we really want to do, and there are a number of different ways to find slope, but what we really want to do is find what we call the change in y, and we want to make that a ratio to the change in x. And this x and y will vary based on the problem that you're working. So in our case, our x is years. So how are the years changing as it relates to how the population is changing? So we're looking always, when we're doing a slope, we're looking always at a ratio of the change in this vertical value, the vertical or the y value, how does it change, as it relates to how the x changes or the horizontal value changes. And we use x and y just because those are our common variables to be used for input and output. So what I'm going to do is I'm simply going to look at the change and do a little bit of arithmetic and say, okay, that population went from 230 to 313. So 313 minus 230 tells me that the population changed by going up by 83 million. So 313 million, subtract 230 million is 83. And of course this is in millions, but we'll just worry about that in a few minutes. All we are really concerned about right now is, what is the numerical change, and it is 83 million. So our population changed by 83 million. And you could write the word million there, or if you wanted to even write out the zeros to make that a million, you could do that. Now, how many years went by over this course of time? Well, from 1981 to 2011, that's a 30-year period. I get that by doing the same sort of thing. I subtract 2011 minus 1981. That's where I get my change in years to be 30. Now, this is actually the rate of change. And that is that the population increased by 83 million over a 30-year period. Our change in y over our change in x was 83 million additional people over the 30-year period. And this is a rate of change. So often when we're working with the slope of a line or the rate of change of something, we want to get what's called the average rate of change. And so we, instead of looking at this over a 30-year period, we'd like to look and see how this changed per year. So if we could find the change in the population on average, which is why it's called the average rate of change, per year, then we would be able to call this an average rate of change. And so to do that, I'm going to take the 83 million people that I had, and I'm going to divide that by the 30-year period. And what this does is this reduces this down to the average change per year. And so you can see that's about 2.77 million. 2.77 million per year. So each year over that 30-year period, the population was changing an average or increasing an average of about 2.77 million. And you can see it's not exactly that much. I've just rounded here to answer my question. But it's a general idea of what was happening on average each year. So my final answer here, and you could write out the 2,766,666, or I guess it would be 667. Per 1 year. And we just did that as an approximate 2.77 million additional people added every year over the 30-year period from 1981 to 2011. So now I want us to look at some more general things about slopes of lines, just so you get the idea of the kinds of situations you may see. There are really only 4 types of slope. So I'm going to label these 1, 2, 3, and 4, and then we can talk about each one. The first type of slope is what we just saw, and that is a positive slope. Now, when we have a positive slope, we'll have a line similar to what we saw with the bar graph. Let me just page back up for you to see that. Notice that that bar graph shows an increase from left to right. Well, when we're working with lines that increase or go uphill basically from left to right, we describe that as rising from left to right. And we always read our lines from left to right. And when we are rising or we have a positive slope or rate of change, we can also say that the values on the function, after all, this is a linear function, the values on the function are increasing. The population increased over that 30-year period. Now, that is not always the situation. For example, some folks may be looking at their 401ks right now, their stock market, their retirement accounts, those sort of things, and they're seeing that those values are falling. And so if they were to look at that over the last year, for example, or the last few years, they would see that their account values would have a negative rate of change, a negative slope, if you will. That means as you move along the line from left to right, and remember, we're always moving from left over to right as we read our lines. When we do this in this case, we see that this line is falling. So if I were just to pick two points at random along this line, I would see that the value of the y is falling over time. Starts up here. Again, I'm looking at the y value. Starts up here at this point. Ends up down here at this point. So it's falling. negative slope, the picture will be a falling line from left to right. We call this a decreasing rate of change, decreasing slope, if you will. And those are the two probably most common situations you see, although there are two other kinds of slopes that you may encounter. This third one being what happens on a vertical line. This slope is actually called an undefined slope. And I'll explain to you, and you'll see numerically in just a few minutes, why we call that undefined. And remember, as we're describing slopes of lines, we're describing, is the line rising? Is the line falling? How fast is it rising? How steep is the line? How flat is the line? So when we look at a line like this, we recognize, it's very, very steep, but it's not slanted either in the positive direction or the negative direction. It's straight up and down. Because of that, we say that the slope is undefined, and this is going to be a vertical line. So whenever you have a vertical line, you have what's called an undefined slope. And that is because there's actually no change at all in the x value, or the denominator of that ratio we call slope. Again, we'll see this numerically in just a few minutes. Whenever we have a vertical line, the slope is always undefined. Then our last situation over here is this line. I'll put a couple of points on that line. It doesn't matter where the points are on that line. You'll notice that that line is a completely flat line. And in this case, we say we have zero slope. That's a horizontal line. Anytime you have a horizontal line, you have what is called a zero slope. No rise in the line. And we say that that slope is actually zero. And again, numerically, we'll take a look at each of these examples, and you'll see why this one turns out to be zero versus the other one turning out to be undefined. So let's find the slope of this line. Now, there are really two ways to find slope when you have a picture like this. One is to use a formula. The other is just to calculate rise over run. Remember earlier we said that the slope of a line is the change in the y over the change in the x. Well, the change in the y is describing the rise or fall of the line. So we actually call this rise. And just keep in mind that rise can also be fall, because to get from one point to the next point on the line, you may actually have to go down, which is exactly what we see in this case. And then the denominator of the slope is always the run, and that's the change in the x. So as we run along the x-axis from left to right, what is the change in that? So you really can just use your counting ability. If you have a graph like this, you just start with your first point and you calculate what has to happen to get from the first point to the second point. And so I'm just going to take a look at this y-axis. I'm dropping from 5 down to -2. 1, 2, 3, 4, 5, 6, 7 units down. So in this case, we actually say that the rise is -7, which really means the line is falling. And you can see as it goes from left to right, as we described, if it's going downhill, it's going to have a negative slope. It's a decreasing function. Now we have to look at the run. So along the x-axis, starting with your original point, it was located here at -8, and we've moved over here to 5. How far on the x did we move? Now be careful. This is actually a positive amount because we want to know how far we moved on the x. And so the x actually changed from a -8 to a +5, so it went up by 13. So the slope of this line is actually -7 over 13. So you start at the first point, you go down 7, you move 13 to the right, and you're back on the line. Now we could pick any point on this line and do this. I'm just going to pick another point on the line. There's my little red dot, indicates another point on the line. I'm going to go down 7. 1, 2, 3, 4, 5, 6, 7. I'm going to move over 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm back on the line. That's the way the slope of a line works. You can start at any point, and you can move according to the slope. And if it's a straight line, like we're talking about here, you'll always end up back on that line. Now, I strictly did this by looking at the picture and counting the rise over the run, but there is actually a formula for doing this. So let me show you, using a formula, how you could actually find this. We'll leave our change in y over change in x, and we'll look at the way the formula is written out, and you'll see that we're actually doing the exact same thing. So now we'll use our slope formula to work this next problem. We'll start by writing the ordered pairs for each of the points that we're given. Then we'll apply that formula that we know for the slope. And of course, we could always go back and count rise over run, make sure that we're getting the same answer. So our formula for the slope of a line is second y subtract first y divided by second x subtract first x. Turns out it really doesn't matter which point you call the first point or the second point, but it's probably in your best interest to just go ahead and read your points from left to right. So that's going to be x1 and y1, and this is going to be x2 and y2. And it's just a matter of filling in the formula and recognizing we're still doing rise over run. To find out what the rise is, we take the second y, 8, subtract the first y, -4, divide that, or make a ratio of the difference in the x's, second x minus the first x, 2 minus -4. Pay close attention to your signs. Whenever you have subtract a negative, this becomes a positive. Same thing happening here in the denominator. So in the numerator, 8 plus 4 is 12. In the denominator, 2 minus -4, or 2 plus 4 is 6. And our slope is actually 12 over 6. Rise 12, go to the right 6. Just do a quick check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. To the right 6. 1, 2, 3, 4, 5, 6. Back on the line. So up 12 to the right 6. That's our rise over run. That's our slope. This will also reduce. This fraction, 12 divided by 6. Treat it just like any ratio or fraction and just reduce it. Well, that's going to reduce down to a 2. Now, just because we've reduced it doesn't mean that that's not the correct slope. It is the correct slope. Start anywhere on this line. So start anywhere on the line, go up to the right 1, you'll be back on the line. Up to, back to the right 1. You're still on that line. Slope is 2. Positive slope, increasing from left to right. Rise is 12, run is 6, reduces to 2 over 1. Now here's that situation with a vertical line. And we said, anytime you have a vertical line, you have an undefined slope. That's true. But you can actually do this one by the formula as well. And when you do it, if you'll remember a basic arithmetic fact about the division by 0, you'll recognize why this is undefined. Identifying the points. 3, 8, 3, -3. Do the subtraction. Y minus y. Now, it doesn't matter which one of these you choose as the first point. simply because there is no left or right point. These are lined up perfectly vertical. So I'm just going to start with the top one. 8 subtract a negative 3. Divide that by 3 subtract a 3. Once again, we have the situation of a minus, or subtract a negative becomes a positive. 11 over 0. You rise 11, but you don't run left or right at all. So what does that mean? Well, division by 0 is undefined. Undefined. And technically, we didn't even have to go through the motions of this formula, because whenever you see this line that's going straight up and down, vertical line, undefined slope always.